So thank you for the invitation, and I will then switch to full screen mode, which means I will not see myself, but this is not a big problem. The topic what I am talking about is large values of the remainder term of the prime number theorem, and I will immediately see what I mean exactly by these large values. First, we have to remember the explicit formula for primes, and then delta x is the remainder term of the prime number theorem. And we see that this depends on zeros of the zeta function, and which I will always denote by beta plus I gamma. And we can restrict our attention to zeros with height less than x. And then we see that the oscillation, what I can say, caused alone by a zero rho is x to the beta divided by the modulus of rho, which means that asymptotically it's x to the beta divided by gamma. Now Littlewood raised a problem which perhaps is not clear why he raised it. Prove an explicit oscillation result for the remainder term if we suppose the existence of a hypothetical zero with real part at least 1/2, and for simplicity with imaginary part positive. Now the reason why he raised this problem was that earlier the best result was a consequence of the Fragmin-Lindelöf theorem, and it had two drawbacks. One was that the bound was just x to the beta minus epsilon, so smaller than the oscillation caused by the zero. And secondly, even this weaker bound was ineffective. So that means if we even knew the existence of a concrete zero or a hypothetical zero, we could not say from what point on and what size is this oscillation. And this problem was then, this is due to the possible interference of the zeta zeros, which means that if I consider sum of complex numbers, then I cannot be sure that the sum of these complex numbers can be estimated from below by any term of this sum. So that means if we have positive real numbers, then actually we can estimate from below the sum by by any term of it. But if we have complex numbers, then this is naturally not the case. Now, in order to settle this case, this was, I don't know whether for which particular problem, but actually in order to settle the problem of interference of complex zeros, Turan developed his method, Turan's power sum method, and this was the most frequent tool used in these investigations as well. Now, just a remark that if we consider zeros on the critical line, which we know that there are a lot of zeros there, then we get an even larger oscillation than the one caused by any single zero itself. Namely, we can gain a factor 3 times iterated logarithm of x, which I will denote by log 3x. And even this oscillation occurs in both plus and minus direction, in both direction, which actually disproved type of conjecture of Riemann, which appeared in his work, where he thought that at least the second form of the remainder term, which appears here, this pi x minus Li x, is oscillating in both directions. Riemann thought that pi x is always less than Li x, and this was just in the same year 1914, when Littlewood proved that this oscillates in both directions with a size even bigger than the oscillation caused by a single zero. Interestingly, in the same year, Lehmer showed that at least for up to 10 million, px is less than Lex. And now we know that at least until 10 to 20, really px, pi x is less than Lex. But we will not concentrate on sign changes now. So we will concentrate just on the size of the, so the absolute value of the remainder term. And in this case, it is not so critical which form of the remainder term we consider. So we will work with this delta x, which contains, as you see, the prime powers as well, and therefore it doesn't appear this negative effect, which makes pi x less than Lex usually. Now, if we define with dy the average of the modulus of delta x, and with s of y, the maximum values of the modulus of the remainder term for x less or equal than y, then Turan succeeded in 1950 to solve Littlewood's problem, and the lower bound is really bigger than x, y to beta naught minus epsilon. So there is a concrete explicit function, and it is also explicitly given in dependence of the row from which point this estimate is true. Now, some 8 years later, or 9 years later, Knapowski proved the same for the average of the remainder term. The method in both works, the most critical part is Turan's power sum method. I mentioned already that complex numbers, if we have complex numbers, and their sum might be much smaller than the largest term, for example. And Turan worked out a method which up to some extent helped to face with this situation. So in some sense, with a factor, what we will see later, he succeeded to neglect this possible interference of zeros. So this result of Turan, which was used in both his proof and Knapowski's proof, was the so-called second main theorem of Turan's power sum method, that if we consider power sum of n complex numbers, we use a normalization that the largest of this number has modulus 1. And then if we consider, we cannot state naturally that for every nu this value should be large, but what we can state, and this is what his second main theorem states, that if we consider at least n values and consecutive values of this exponent, then apart from a very significant factor, which is much less than 1, we will reach the bound 1, and we have still a factor depending on these coefficients bj. Now, in the present problem, we don't need any coefficients. So that means we have a special case of this Turan's second main theorem, which can be written in this case so that the New's power sum of n complex numbers taken, if we take the maximum value for n consecutive values, then this is a function which depends exponentially on the number of variables, and it depends somewhat less drastically on the beginning of this interval. Now, one can easily see that if we consider, for example, nth root of unity, then we have n minus 1 consecutive values always, which are exactly 0, and then we have one which is large. So that means we, in some sense, this result is optimal, and we don't know whether the lower bound is optimal or not. I used not exactly the same result, but a similar argument that means it was more generalization of Dirichlet's approximation theorem, to show that if we consider oscillation, then this oscillation is really, apart from a factor 1 minus epsilon, the oscillation is x to the beta naught divided by rho naught in modulus. So that means the oscillation caused by a zero occurs really from time to time, and this seemed to settle, so to say, to be precise almost completely, the oscillation problem of delta x. And here this function C2 of rho naught and epsilon was effective as well. The proof used Turan's method in, not Turan's power sums, but it was similar to the way Turan and Knapowski handled proved their results, but the difference was that I used another approximation theorem, and I use still the general framework of Turan's result. Now, immediately there is a question that what is the optimal oscillation result? Because we know that we have two zeros, two conjugate zeros of the zeta function always, and therefore I thought also that 1 minus epsilon could be replaced by 2 minus epsilon, and this would be really the case if rho naught was isolated, if we would not have nearby other zeros. And then the question was up to some extent or almost completely really settled by Szilárd Révész in '83. He showed that we don't know what is the optimal constant for the zeta function. Naturally, if the Riemann hypothesis is true, then the optimal constant is infinity. We remember that we have then an oscillation of size log x times the log x times the term any zero on the critical line. And so then this question is interesting just when Riemann hypothesis is false, and so therefore it is very hard to say even how to say mathematically precisely what we mean by the optimal constant. Now he proved that the optimal constant is pi over 2, which meant that pi over 2, the result which I stated was true with pi over 2 minus epsilon instead of 1 minus epsilon on one hand, and on the other hand, if we consider a wider class of functions which include the zeta function as well, then at least for this larger class of functions, there are some functions for which pi over 2 is really the optimal constant. We could formulate it also that there could appear such intricate configuration of zeros of the zeta function so that the oscillation would be really not exceed pi half minus epsilon times the expected and proved value x to the rho naught over rho naught. Now, I proved also several results on with other methods, both for the average and the maximum value, thereby improving the earlier results of Turan and Knapowski. Also, Schrager-Puchta showed such an improvement. And what our goal is, that naturally different forms of these theorems had different conditions. concerning the dependence of y from gamma naught. That means from if rho naught is given, and then from which point on can we assert that the average or the maximum value is large. Then a lower bound as a function of y and gamma naught. That means how large is really the average or the maximum, dependent on gamma naught. A third problem is that whether this large values occur just somewhere between 1 and y, we can state that the average or the maximum is large, or we can say that they occur up to some extent near to y. So that means near to y means unfortunately not near on the normal scale, but near on the logarithmic scale. So that means that the logarithm, if for an interval of the form ay to y, and this beginning of the interval ay should be at least on the logarithmic scale near to log y. Now again we can consider effective or ineffective estimate, and another method of mine gave a result which produced a lower bound which depended on the derivative, on the absolute value of the derivative at the place rho naught, which for concrete zeros, which we know is really completely okay, but it would be already somewhat disturbing, so it would make the theorem, let's say, a little bit ineffective if we speak about a hypothetical zero, and this could cause problems in some applications. Now, I mentioned already that the really difficult cases when the really interesting cases when the rho naught is not on the critical line. That means the Riemann hypothesis is really false. Now, I mentioned just some results in this direction. I proved that actually we can always reach that not only we have values as large as y to the beta naught divided by y to the beta naught divided by rho naught, or x to the beta naught divided by rho naught sometimes, but also that the average is at least y to the beta naught multiplied by some constant depending on the imaginary part of the zero. And this has the corollary that on the Riemann hypothesis, the average of the remainder term in modulus is at least square root y, or the average is square root x. Now, Kramer showed already exactly 100 years ago that on the other hand, the average of the remainder term in absolute value is at most constant times square root y. So we know exactly, apart from a constant, the order of magnitude of the average order of the remainder term, supposing the Riemann hypothesis. This is this estimate here. And on the other hand, this is still unclear, the maximum value of the remainder term between these two bounds. Now, this actually served as an introduction for the theorem, for which I will also sketch the proof, namely that if we have a concrete zero of the zeta function, and we know that y is enough large, depending on an explicit way from the imaginary part of the zeta. I just mentioned that already. I mentioned that, but emphasize that all these constants C will be explicit constants. In this case, we can localize, we can consider the average of the remainder term in modulus, and localizing the average in the logarithmic scale from a beginning point near to y until y, and we get for it a lower estimate, which is just with a factor log y square smaller, x minus log y square smaller than the expected value. And concerning the localization, I lose again the same log y squared quantity. Now the strategy is that we consider a weighted mean value. That means, as I mentioned already, concentrated to interval ay, y, where log y is near to log y. We already specified that actually this ay would be this quantity, so log ay is less than log y with a quantity log y square. Now, this weighted mean value can be transferred into a sum of residues containing the zeros of the zeta function, and up till this point, the strategy is same as by Turan, Knapowski, and in my earlier works. The novelty is that the weight is chosen so that only zeros very near from rho naught should get non-negligible weights. And in this way, we can avoid both Turan's method and both the loss which is caused by using Turan's second main theorem. This means this quantity, what we have here, this is actually a loss compared with the expected value. And naturally, due to this averaging process and due to this procedure of getting rid of other zeros near to rho naught, we have also a loss in the procedure, but this loss is just a function x minus log y squared, whereas in the works of Turan and Knapowski, for example, they had a loss of log y divided by log y, and we have instead log y squared, so we have a much smaller loss than in the procedure of Turan and Knapowski. Now, in the present method, we will, what I said, we will get rid of zeros not very near to the critical given zero rho naught. So that means we will construct a weight function which is asymptotically the same for a small group. Group by group, I mean just a set, so there is no group operation here. So for a small set R of zeta zeros near to rho naught, it is asymptotically the same. Naturally, these zeros are very near to rho naught. Then at a distance, basically this C naught, we can say it's 5. So at a distance at most 5 for all the other zeros, the weight function will be just 0, and in this way, those residues will not appear at all in our work. And due to other part of the weight function, the weights will be not 0, but negligible, the weights for the residues, if we are more far than 5 from this point. Now, in fact, the original theorem was formulated in such a way that the upper bound was y. Now we consider on the logarithmic scale an interval symmetric to y, and this will be our estimate. And here what we should possibly keep in mind is that script L is log y squared, lambda is log y, and L is log y. So capital L is log y, lambda is log y, and script L is log y squared. And script L is which in the exponential scale appears both in the loss and both in the localization. And this will be the exact form in which I will prove our result. And the beginning is a procedure what was observed by Turan, that if we have a zero and we have near to that zero, near means just that on the logarithm, on the height is not too far from it, but the zero is a little bit more on to the right, then we take this other zero instead of our original zero. And so with step by step, but the number of steps is at least at the most just log y, or we can log y, we can go further to another zero, what we call an extreme right-hand zero. And this extreme right-hand zero has the property that its real part is at least as large as the real part of the original zero. So in this oscillation theorem, we just gain by it. The imaginary part can be somewhat larger, but this is not decisive, and still we have a control about it. The original imaginary part was at most square root of lambda. And by this procedure, it will be just lambda squared, and lambda is just log y. So that means it will be still near to log y squared at most. But on the other hand, more on the right. And this is an important point of view, that for this zero, we have already, if we go a little bit far to the right with a quantity 1 over log y, then we will have a large, so we can, if we go a little bit more to the right, then already in the, how to say, vicinity, but not vicinity, but in a rather large height, so that means 3 times log y higher or 3 times log y lower, there is no zeta zero as at all. So that means in some direction, at least, we solved the isolation of rho naught, but we are very far from saying that rho is an isolated zero. So this procedure is just, how to say, a routine used always by Turan, Knapowski, and also myself in these works. And this is just a nearly trivial starting point for the procedure. And if so, that means our final zero is this gamma wave k, beta wave k, rho k wave. This is what we substitute the original rho naught by this zero. But then comes the idea is that we take a very small epsilon, and then we consider zeros which can be reached from one from the other by a chain of zeta zeros, so that neighboring zeta zeros are at a distance at most epsilon from each other. But this epsilon is not a small absolute constant, but this epsilon is something which is very small. So first we consider already zeros which could be reached from each other by a chain of zeros, at most with a distance at most, as you see, 1 over log y, and this is even in the denominator multiplied, so that means this 1 over log y to the 3rd power. So these zeros are very near to each other. If in this group there would be just 1 zero, then this we could with right call an isolated zero already, and then we could so to say go further with this procedure. But what we know just is that it might be, so that means definitely the starting set of zeros was contained at most log y, that means L zeros, This is by the result of Beckland. And this was later, we can, so to say, nest into each other smaller and smaller groups of zeta zeros, so that they would be very near to each other, but any zero outside that small set would be much more far from these zeros than those zeros are from each other. So that means this whole, we repeat the same procedure and we take always sets which of zeros which could be reached, so equivalence classes of the zeros which could be reached from other by a chain with a smaller epsilon 2. Smaller means by a factor log y third smaller. And if we always consider and continue our work from the smallest set, then this whole procedure must finish quite soon. So the number of steps should be just log L. That means much smaller, and in this way we will get very soon just really not an isolated zero, but a set of zeros, what we will call R by R, with the property that they are very near to each other. Any other zero is already much further from it. Much further means still it may be a small distance, but much further with a factor log y to the second power. And then we consider an arbitrary zero from this set R, and we will have, so that means basically the same extreme right hand property will be true for this zero, maybe with a little bit changed parameters. And afterwards we consider a polynomial, we construct such a polynomial, which is, so to say, since the residues will occur at the places ρ1 minus ρ prime, so that means in this way we will get such a polynomial that if we consider any other zero which is not in this small group but at most a distance 5 from it, then we will have a property that will be interesting in our case. So that means if we are not in this small set of equivalent zeros, then the polynomial is 0, and we have, so this is one thing, for those zeros which are in this small group, this polynomial at the place ρ minus ρ1 is asymptotically the same, exactly 1 plus order 1 over log y. And we know bound for the value of this polynomial at different places, roughly speaking, e to the L or s absolute value to the L. So on in an exponential scale, we have this L, which is log y squared, L squared, 10 times or 40 times, I don't know, 100 times, I don't know. This is the value of L, and this will be equal e to 40 times L will be the actual loss in the procedure. And so this L will have an important role, but that means we have a control over the size of the polynomial. And here comes really the weighted mean value of delta. We consider this delta x divided by x to 1 plus ρ1 times weight on the value y over x, So that means this is also in some sense on the logarithmic scale. And the weight function is defined together with this GS function. And the GS function has three factors. The first factor is relatively small if we are, let's say, at a distance at least 5 and at most log y from the 0. Then if we are at least a distance log y from the 0, then this factor will be very small. That means negligible. And with this PS, we have a control over its increase along the imaginary axis or along any vertical line. And we have this property that the rho minus rho 1 will be just for those zeros for which the value is naturally very near to 1, then for those zeros will be 0. And so I go back to this, that the polynomial will be 0 at these points, which are very near. No, the polynomial will be 0 for those zeros which are not very near to the distinguished rho 1 in this gamma less than gamma 1 less than 5. And the polynomial will be at the places rho minus rho 1 nearly equal to each other. So that means the residues will be nearly equal to each other in this small group, for the small group of zeros. Now, one can show relatively easily that this weight function, which is defined by an integral, what we can do, that if A is large, then we shift the line of integration onto the left. If A is small, we shift the line of integration into the right. And if A is, so to say, in between, that means not too small, not too large, then we integrate on the line, on the imaginary line itself. And then due to this factor, which is sigma square minus t square, an absolute value, this will be very small if we are far, at least the distance log y from the 0. PS takes care to eliminate the residues at the zeros which are near to rho 1, but not very near to rho 1. And this factor will take care for others. But now, considering just the weight, it is still, this property is not needed, just the way how quickly the polynomial p might increase. And what we get will be that we will get either a very small quantity, lambda is just log y, so this would be the same as y to minus a, for example, and this will be very small if a is large. This will be very small if a is small, and in between we have again the same e to the l, which is up to some extent lost in the procedure. And this is the way how we show this. And so that means it is a technical question. Now, if we know this weight function, then we can already estimate the weighted mean value of our original uy, which was defined earlier in this way. So that means delta x divided by x to 1 plus rho 1 multiplied by these weight functions. And then this weight function has the property that it localizes the whole integral just for the range y times e to the minus l to y times e to the 2l, apart from a loss of a factor e to the L. And so that means that we can really forget about the tails of this integration, and we get a localized average of the delta. And this is exactly this Vy, what we will, in this way, we can connect the localized average with the full average of Uy. Now, if we go further to Vy, then this Vy can be, which is a weighted mean value of the remainder term, can be expressed by an integral, and this integral is can be proved easily by partial summation. We get a logarithmic derivative of zeta there, and this means that the original mean value, as we see here, if we change the integration in this way, then we get an integration for the function hs plus rho 1. So we get an integral here in this way, and we see that the residues occur at the places when s plus rho 1 is equal to rho. That means if s is equal to rho minus rho 1, and this gs is small if rho 1 is more far than 5 already from the original point rho 1. This p is equal to 0. That means g is also equal to 0 if rho is not in R, but I forgot to write here. No, it's here. If the distance is at least at most 5, in this case, this polynomial p takes care for eliminating the residues at those zeros which are not in R. So these are the zeros which are at a distance at most 5, maybe quite near to rho 1, but not very near in the sense that not in this small group R. So in this place, the function is analytic, and this means that we get actually a type of, we can call it a power sum, but I'm not quite precise here because I should write here that rho is not equal in R plus no, that's okay. That for all the zeros which are not equal to, not in this size very near to R, and but fortunately, let me see. Not in R. Yes. So that means, pardon? Yes. Okay.
Yeah, please continue, János. Christian should ask the question after your talk. Yes, that's better.
Thank you. Thank you. So that means in this way, we have the residues for all the zeros of the zeta function, which are not near, not very near to the original rho 1. And in this way, we will get, so we can call it a power sum, but the value of this, to evaluate this power sum is very easy. Excuse me for a moment, yeah. Yeah, so Uy is, so Uy is, contains zeros which are, so this is not correct, that rho not equal to R. Yeah, this is not correct. We have zeros which are very near to R, plus we have zeros which are at least a distance 5 from R. So that means these rho not equal to R, not in R, these are Arrhenius. Maybe the question referred to this. So we are some zeros which are, so if we consider the zeros which are, so to say, at a distance at least log y, then we get y to -2 as an upper bound here. If we consider zeros which are at least 5 from it, then again due to another part of the g function, we get again something relatively small, not so small like here, but relatively small. Now, what appears still, what remains still, is that for those zeros which are in R, we get asymptotically one for each zeros, and so we can evaluate easily the power sum for R, and as I mentioned, the zeros which are not in R but at a distance at most 5, they don't appear at all. And in this way, we get for this power sum, we get exactly the lower estimate, and we get by this lower estimate, we can prove the original theorem as well. And thank you for your attention.